start by welcoming everyone. It's so good to see you in the new year. This is our first series of the year, and I am happy to start us off thinking about how we can best measure our essential traits for all of us who are in breeding, in the breeding community. We do understand that phenotyping for our traits is a big bottleneck, and we're always working towards exploring new methods and approaches to overcome this. So today we're honored to have Lennart as our guest speaker. Lennart is the project leader in digital solutions at Alliance Biodiversity CGIAR. He leads the project Artemis, and he's going to talk to us today about the innovations that are being developed towards measuring plant traits. So Lennart, feel very welcome. Thank you so much for accepting to speak on our platform today, and I will hand it over to you now.
Yeah, Dorcas, thank you so much for this opportunity. I think it was Bish that told me that, hey, this is a very good platform to talk about the work that we're doing, and really thank you for accepting us. So I am not the project leader, that is David Guerena. He's also better versed than me in breeding. So I hope I do justice to this group in that sense. But yeah, so my name is Lennart Woltering. I'm a scaling expert. I've been working the last 7 years with CIMIT. I was at Ecrisat before, and then I was in the private sector. Now, since last year, I'm with the Alliance, providing strategic advice on scaling the Artemis project, which I'm going to talk about today. So let me share my my presentation. Yeah, I think, can you see my screen? All right, can you see my screen?
Yes.
Yeah?
Yes,
Okay.
yes, thank you. Yeah.
Okay, thank you so much. So, yeah, the Artemis project, it's implemented by the Alliance and supported by the Gates Foundation for the last, almost 2.5 years now. We started off with IITA, and then now recently we're working much more with CIMIT and SIP and TARI and Google Research, as well as part of a whole ecosystem around Artemis. So what I want to talk about today is, first of all, why Artemis, why smartphone AI-powered phenotyping tool. And then I want to talk to you a bit about the research process that we've been going through around two hypotheses. One is around the accuracy, and the other one is about the efficiency. And then what that means for the value proposition that Artemis actually presents. Then, of course, a few words about my favorite topic, the scaling strategy, and then some next steps that I want to discuss. So, yeah, classical phenotyping for, maybe hundreds of years is basically based on human observation and rather qualitative estimates of what's actually happening. And if you look at where we are now, machine observations or artificial intelligence supported solutions that are being applied or have been applied already a lot in private sector, using machine observations and turning that into quantitative counts. And that makes it easier to integrate into a whole breeding pipeline, because if your data collection, that quantitative data can go into cloud, and then in whatever analytical system of choice we can say, for example, the enterprise breeding system, that quantitative element makes it much more smooth, right? Now, if you then again look at, okay, well, what is going on in this area? And one of the first thing that we started with, I think with CIMIT 5 years ago, is looking at rovers, right? This is what big companies are having, and we said, okay, we also want to try this out. Employed one in Colombia called Don Roberto. It's a bit of a name joke in the Latin America style. But this is actually kind of like, whoa, this is the thing that works and is being used everywhere. But as with many things that are so fantastic, they have great strengths, right? You have fantastic pictures, multiple cameras taking pictures of crops, very accurate models applied widely around wheat, maize, and beans, etc. But yes, very expensive, specialized maintenance. It broke down in Colombia and was sitting still for at least 6 months because you cannot find exactly that bolt for that tire, etc. And it's not really scalable. So it's rather like a transition technology to something a bit more practical. And therefore we kind of settled, okay, well, this what we have there, which we see working in the field, this needs to work as well on a mobile phone. So that's basically the big challenge that we set ourselves in the Artemis project. How can you make this work on mobile phones? Affordable phones, why? They're affordable, they're scalable, and they're kind of everywhere, right? But of course, not every smartphone is the same quality. I mean, we all know that the one that you have may not be the same as some of your friends. And it may also be challenging for really efficient throughput, right? Just the thinking power, etc. So, like I said, we focus first on the accuracy of computer versus human vision. Can you actually do things as good or even better than what humans can do? So that was the first thing that we tried to figure out in the project. And here you see a graph where you look at, let's say, this is one plot, this is the same plot the next day. So we have here for 6 different plots that we looked at. And we looked at, okay, well, how many plants per plot are there? And this actually shows the distribution by the number of people, by a few of the technicians that measured it. So you can see that even across the days, there's quite some variation in here as well, right? There's even with just the same amount of flowers or plants that are there, people have counting very, very different numbers. And just also look at just a different day, what people are finding. And you see that even with the pot counts, which is a bit more difficult, for example, if you have a bean, then you need to, of course, look under the canopy, etc. It's a bit more difficult than counting how many plants there are. You see that the distribution is even bigger. So between the people that are counting, there's a lot of variance. If you ask Paul, he will say 5. If you ask Peter, he will say 20, right? So the challenge is then, okay, if the human accuracy is actually not that high, can we solve that with computer vision, right? And you see here a smartphone taking a picture of plants. And we said, okay, even though you have something accurate, it needs to be efficient as well. Otherwise, it's never going to be scalable, right? So we looked at ways of making the computer vision more efficient, and we did that through a small device called Bruno. And I'm introducing it now because in the data that I'm going to show, this comes back. This kind of one wheel device where you can mount 2 phones or 4 phones or or 6 phones. We're still kind of playing with that. So if I talk about handheld, then this is the one where you just walk with a smartphone. And if I show you tables where it says Bruno, then this is Bruno. And basically what you could see is that, okay, if you take pictures with a handheld, it's still quite a lot of time. like I said. And if you do it with the Bruno, if you image a plot, it is still, sorry, what I'm trying to say, if you do it with a handheld, yeah, it can still take 1 hour to image 10 plots, right? So that may not be that much faster than, you know, not using a phone, right? But if you then look at what Bruno can do, you can actually do this within 30 seconds, right? One plot. So if you then look at 10 plots, that's then 300 seconds. But you really drastically increase the efficiency by using Bruno. Just putting that on that card is much faster than walking through the plots. And then we look at the mean average precision for some of the training models, looking at the different traits and the different models. So I think one of the key messages from this is it's a very colorful picture, but it basically shows that, okay, plant stand, the difference between the visual estimation and then the what the computer vision model can see is rather high. You know, what the human can see more easily, the computer can also see more easily. But if you then look at open flower count, you know, is there a flower and is it then also open, which is more difficult to see. Also, the computer vision models have more difficulties with that. And you can see here that there on the right, the different colors show that there are different models out there. And this probably picture couldn't have existed, let's say maybe 3 years ago. All these models didn't even exist. So this is rather new and all the time evolving. So one of the things that we're also doing is not saying, okay, computer vision does this or that. There's also a difference between the different kind of models that are out there. So here you say, okay, the computer model identifies very accurately, and here not so, right? So, and also what you can see, doing it, for example, for beans, seeing how many plants there are, is easier than, for example, with sorghum, right? So the plants are much closer to each other. It's much more difficult to see. The leaves are much smaller. So if you then also talk about how do you train those models to recognize that this is a plant and this is not a plant, you need much less pictures with the beans than, for example, with sorghum to train those kind of models. It's much harder for the computer to learn it. Now, like I said, if whatever the human sees easier, the computer also sees a bit easier. For example, the pod count, that is more difficult for a computer also to see than, for example, the stand count, right? But what is interesting is that the computer actually is pretty good at recognizing what is a leaf, what is a pod, and what is not a pod. This is easier here with beans than with cowpeas because these stems of the plant, they look a little bit like the peas actually, right? Like the pods. So again, here you also have to kind of then say, maybe we need it, not maybe using boxes like we do here, which is an easy method. There's also a different way of segmenting, just to show that even with the computer vision model, within that, there's a lot of experimentation, trial and error on what is the best method then to actually recognize or recognize, yeah, whatever we see in the image, right? And this image just shows that, okay, you don't need a lot of training images anymore than maybe like a few years ago where you had to have 10,000s of pictures to kind of train your model. Now you can train your model with much less images because the models behind it are so smart, much smarter than before. So this is a bit of a similar point, just to show that there's so many different models again to go from that one image, that you took of that plant, that needs to be translated to a plot level, right? And there again, there are like various models that you can use. And just to show that this is something that we were also looking into, okay, which model then works best for that exercise. And what you can see is that with the different, for example, with Bruno, the heritability actually goes up because you can filter out more the human error because there's less human error, so you have more the whatever or variance you see is much more due to the genetic component, right? And I think the same message is there with the blobs method, is that they do pretty well compared to the ground truth, especially the Bruno. And let me check what I wanted to say here. Yes. So yeah, also the correlations here with the different methods that we have is pretty high correlation. So yeah, pretty good basis to make some breeding decisions on. Now, so that's pretty technical, and I was explaining that you can increase the efficiency, you can increase the accuracy. But what does that mean now for Artemis? What actually does it mean? What does it mean for what we have in our hand? And we reached out to the at that time still the Excellence in Breeding team, and I think maybe some of you are there also. We said, okay, well, what if you would compare this way of doing phenotyping with, let's say, the more traditional way of phenotyping? What does that mean in terms of cost saving and value generation? So we were really happy to find out that I think the University of Queensland, together with the CGIAR, has developed very good data collection models or data systems around what the costs are for basically setting up some advanced yield trials. So we looked at those together with the EIB team, now the breeding resources. And what we could see is that, well, first of all, if you look at an entire trail, the most costs are actually more in seed preparation, site establishment, and agronomy, right? So it's not all phenotyping, which is expensive, right? Phenotyping cost is about 25% of the costs of a trial. Almost the same cost as harvesting, right? And then we said, okay, well, what if you then make phenotyping more efficient and you do that in the way that we are proposing with computer vision? You can see, okay, well, not all the traits that you're phenotyping can be taken over by the Artemis tool at the moment, right? It's mostly the counting traits, but not something like dry matter weight or yield, etc. That's still like done with a scale. So we didn't calculate that. So we said, okay, we just assume that you can do the counting traits and disease here. And then we looked also saying, okay, this doesn't only affect phenotyping, but also the breeder can travel less to the field because you're using images. And with the dashboard, you can see those images in real time. So a technician takes images of the field. So you can see actually what that person is seeing and why he's scoring the way he's scoring, which allows you not to go to the field so many times, which is one of the major and important costs for transport, etc., and in terms of time saving for the scientist. And then, of course, data analysis, because you have, let's say, one uniform way of data collection, all with that same app. You save quite a lot of time in terms of collecting the data, waiting for it to be harmonized, etc. And then, of course, with the Artemis technology, with the dashboard, you could do some basic analysis as well. That's one of the things that we are developing. So all in all, we found that the scientists can save like 54% time and data collectors save around 40% of time. So overall, you have a 50% cost saving on phenotyping. And if you look at the entire advanced yield trial, in the case of that case of Nigeria we took, where there were 6 sites, you save about 17%. And that means, going from 140 to 110,000 US dollars, for example, right? Now, we looked at well, what is actually the value that you can create from that? Basically, it allows you to add one trial location, the cost for seed preparation, transport, etc. You could add with that saving, you could add another trial location, and you could even add one replication. Now, so we added this in a model that we've been developing together with Violet from the London School of Economics, and saying, okay, well, there are basically a few pathways here that come together. So you have improved efficiency, you can have more replications, and you can have more environments, which increases the heritability. If you then also look at the improved accuracy, you don't have to repeat trials. One of the things that we found, and something I'd really like to learn more about, and hopefully this community is a really good entry point, is what is actually the error that is happening today in terms of phenotyping, or maybe the uncertainty about the quality of the data. So one of the things that we found by just some initial kind of interviews and research is that, look, 20% of the data is often thrown away, it seems, right? This is something we need to confirm more, but that's an initial hunch that we're getting initial kind of feedback from people. And if you also look at if you can reduce the error variance, so normally there's environmental error, but also the human error, and if you can reduce that human error, you'll end up with a shorter breeding cycle, but you also increase the heritability. Now, that translates, let's say, to a doubling of the genetic gain, for example, for pod count, and that then leads through the breeder equation to a higher yield on the farm. So if you look at that, just a very simple way of calculating, very back of the envelope kind of calculating, in the cowpea example, you would gain, let's say, almost $1 million per year in value added from one breeding cycle, right? So this is the kind of the value that we're looking at of doing it. If you combine improved efficiency with improved accuracy. So that's one. Another element that we're looking into, and I think where really the most impact is, or the most also the most interest, is moving from on station to on farm. Okay, see this picture. Yeah, maybe let me go back. So this is let's say an on station, like a station, very nicely, nice farm, everything very homogeneous. And then if you go to the on-farm bit, you see here that there's just so much heterogeneity that's happening on the on-farm, so many differences than what we have on the station. And I'm quoting here some research done by colleagues from CIMMYT, I think a few years ago, is that the correlation between what you have on the station and on the farm is really kind of relatively low, right? So yeah, how can we move, let's say, all this breeding work, how can we move parts of it, or important pieces of that also more to the on-farm? As we showed, the Artemis takes away a lot of the logistical challenges in phenotyping. Doesn't require you to go to the field for example, for a scientist that much. You have very more accuracy in data, less errors, etc. What if you applied it on the farm? And one of the things that we are also exploring through another funding that is also kind of a sister project to Artemis is called, and these where we're basically using voice of farmers to find out what kind of traits they're actually interested in, right? And using large language models that then convert voice, in this case Swahili to text, which was also a bit of an innovative element to it. And with the tone of voice, we could see the sentiments. Are they then positively talking about it or negatively talking about it, right? So they say, okay, these are the kind of traits that they were mentioning, and then they were saying negative things or positive things about it. So this is very early work, but I think it shows a lot of potential, even if you can disaggregate, for example, by gender. And for example, some of these participants, let's say, identified 14 traits, and if you look at men needed to explain this or kind of come to this conclusion, what the model drew from that conversation, they needed 470 words. Well, women said basically the same, but needed much fewer words, which of course maybe a lot of women recognize that men need to talk more to say the same thing as women can do actually. So now we have scientific proof for that. So one of the things that we also found, and this is yeah, very recent kind of findings, is that it's a bit difficult to read, and it's not a point, but it shows that just by using ChatGPT prompts of the text that was generated from those very open kind of, like, not say interviews, but very open discussions with farmers, where a lot of basically data is generated, which you wouldn't ever be able to capture in the survey because it's just too much and too kind of like difficult to capture. You can do that now using these language models, and the yellow ones say are kind of like the traits that we are aware of, right? That we have always been working on. And green are more or less traits that are relatively new or that we don't necessarily breed for. So it's quite a lot of new things coming up, new traits being mentioned by by farmers, mostly on plant architecture or grain and pod characters. So again, allowing a work that's maybe more farmer needs driven. This is, I think, a very nice way of looking at, okay, well, how can you capture what farmers want, but really at a very, very yeah, large scale in a very efficient way, right? So yeah, you can imagine that, having this conversational data, even on, what farmers need, but you can even use it also, for example, by the people that do the phenotyping, not only taking the pictures, but at the same time speaking, saying, okay, I think I'm seeing that this is a disease, this and that. And then that, of course, can be correlated to what the images show. So there's a lot of potential for combining, let's say, the images with the voice. And one of the things that we are doing in Artemis, which is I think important also to remember, is we're not only developing, let's say, a phenotyping application on a phone, but we're developing, let's say, the models behind that. So the phenotyping app is basically a product coming out of that. But another very important product is that actually that foundation model that can then develop pod counts or flower counts for any other crop, right? Because it follows then the same principles that it was taught through the beans and the sorghum and the cowpeas and the other models that we already have. So that's something that we're working together with Google Research on, so that anybody who wants to have, let's say, a specific model for their crop, be it a faba bean or any other crop, can basically take the whole computing engine that we are developing, the different models, all the many colored graphs that I showed, kind of have that done in that foundation model, and then from that you develop your very specific models, but that's your specific applications. But you don't need to do that whole modeling part anymore, or to a large extent. So in our approach to scaling, I think it starts really with, or it started with a very strong focus on human-centered design from the beginning. So this is kind of the research that we've been doing from the beginning, say, okay, well, what actually are the problems? What are the pain points? What are desires of, let's say, the people that we are designing this for, right? The technicians and the breeders and the breeding teams. What kind of background do they have? What kind of skills they do need? What kind of needs do they have? So we went really deep into understanding, let's say, the final user, and also the kind of, let's say, the yeah, the organizations or the breeding programs themselves. So we have very nice breeding cards that show how they work. For example, here in Nigeria, what is the kind of like what do they do? Just all on the one page. What kind of software do they use, right? Do they use Fieldbook? Do they use BreedBase, etc.? So we have this for some of the key centers, and I think it's a very interesting resource. And again, we're using human-centered design also to make the application, you know, as user-friendly and as intuitive as can be. Now, the other element is that I think from the beginning, the Artemis project was kind of designed for scale. Of course, we were talking about a large user base, also looking at quite a lot of investment, estimated about maybe 100 millions per year in the CG just for breeding. So there's quite a lot of scope. We're not looking at, let's say, well, how you can, maybe the Artemis application, the smartphone application is you know, too small for drones and too big for pen and paper, kind of, no? So we're kind of in that niche there where I think the best use can be made of this kind of technology. And we're looking at efficiency. Like I said, we have taken quite an economics approach to this. What is the value? But also looking at accessibility. So in our design, I mean, the Bruno looks very, you know, rough. And that's so because we want this to work, let's say, in Eastern Congo, right? We don't want to design this for the Ibadan research center. No, we want to design this for the small research stations all over Africa and all over the world, right? They are maybe not as well resourced and that can buy a $300 phone, but not a $800 phone, right? So we're looking at really designing it for that. Another element of I think the scale element here is that there are many, I think, partnerships and breeding networks where data collection is an issue and having harmony across the different ways of collecting data and having something that can be used, you know, is accessible for anybody to use and collect data in a reliable and transparent way, I think is really something that has a lot of potential, especially for activating more the breeding networks and having them collect data with one tool, for example. And then compatibility, right? I showed already compatibility with EBS, for example, or with other tools that are out there. Is also important. You don't want to have your own specific thing. So, and the other element, I mean, this has to be also fundable, a fundable initiative. So we're looking at different kind of pieces of what we're doing, seeing them as different pieces of a puzzle. So you have the on-station part and then the on-farm part, and then different donors are interested in funding different elements of that, right? So now we are leveraging money from Google and then from the Gates Foundation mostly, but also other other donors may have interest to support. Now, maybe the most important, we could have started with this as well, I think, and also I think what really excites me about the Artemis work is that they have a very diverse team. With a lot of attention for the product. So it's really about product development. And we have really quite a lot of people that are coming from the private sector with a very strong product focus, product development, and human-centered design, then combined with people in the machine learning operations, and then maybe with the more traditional CGIAR skill sets on field operations and project management. And yeah, of course, with a strong focus on scaling and market research also from the beginning, not something that you do afterwards, but you kind of integrate that already from the beginning. So I think we have a very diverse team and in a way, kind of like a pretty complete team to address many of the challenges that are coming out. So we have that core of Artemis, and we call it the Artemis flywheel, is that the diverse skills of people that are able to work together efficiently. They are able to develop, let's say, the kind of the calculating power, the models, the standard operation procedures, the human-centered design approaches that then lead to different kind of products. No, for example, the phenotyping app for different kind of users now in beans, cowpea, and sorghum. But if you look at that, with that kind of engine, you can do many other things. So we're looking at that team maybe moving from a project more to a separate entity, right? Like a spin-off kind of idea. You can go from a phenotyping app to another product that is actually that foundational model that I was talking about. You can go from focusing on computer vision to the multimodal application where you combine, for example, the computer vision with voice, etc. Right? There's of course wild potential in using it not only for breeding but also for agronomy. If you can say derive from the images and from other models, for example, the yield, you can imagine the application of this for the agronomy and for, let's say, the private sector that wants to know, okay, well, how many trucks do I need to send to this area? Because I know that in 3 weeks the yield is going to be this, right? Based on pictures that people take. So a lot of, an expanding problem space that we can address. And I think a very big one would be, first of all, to do this right on station and then continue to do this as well on farm, especially in combination with other programs that are ongoing, like the tricot approach on 1,000 farms. It's kind of like an ideal platform to combine this with, right? So yeah, I think this is something that, we're already collaborating with most of these CG centers and on these crops that are mentioned here below. Next month we'll have the launch of the MVP, and then at the Science Week we hope to give a bit of more of a demonstration to whoever is going to be there. So yeah, for now, thank you so much, and really interested to hear your reactions and questions and comments. Thanks so much.
Thank you very much, Lennart, for that very nice presentation. I think that's quite on point, given that even the breeding community is also looking into innovative ways of sampling the farms better to represent their target population of environments. And we're looking at how can we do this more efficiently. So exploring such ways is actually a timely enterprise at the moment. So I would like to open the floor to the teams for any questions or comments to Lennart. Just raise your hand and then I'll give you the platform. Okay, Tadesse, please.
Thank you so much. Very nice presentation. In comparison to the drones, have you compared the efficiency in time, also in the pictures? Is there any comparison you have made so far? Because the one that you presented still it demands manpower and it takes some time to go plot by plot. But the drones, we just let it go, send the picture to your computer, maybe rapid and efficient. Have you seen such comparison? Thank you so much.
No, great question. It was kind of surprising, and maybe I'm not long enough into this, but it was difficult to find comparative studies, and I've seen that the IRI colleagues in the Philippines, they have worked more on the drone option and comparing that to let's say the more traditional methods. But that's actually just happened. Like I just saw that like 3 weeks ago. But yeah, I think the ambition would be really nice to show, okay, well, this is maybe more the conventional way of doing it. This is maybe the Artemis smartphone, and then the drone, and then maybe satellite. So I think it would be really nice to kind of segment that market and on how you do phenotyping and maybe what are the pros and cons for each of them, and carve out a bit better, okay, what is actually the niche for smartphone-based phenotyping? What is the niche for drones? What is the niche for satellites? Yeah, that's, I haven't seen that yet, and we have not done that yet, but I think that would be super, super interesting.
Thank you. Any other questions? Comments? Yourself, please.
Yeah, thank you very much. It's a nice presentation. I have a couple of questions. One is just to follow the previous Tadas's question, because this one is now involved people. So they have to go to that two-wheel within the row. And so the human error is always there. I don't know, even when you compare that data, you mentioned human error is out of compared to phenotyping selection. Probably you can just give some on that. The second question is also, I think you mentioned it reduces the breeding cycle. And so I didn't get that one. So how accuracy will reduce the breeding cycle? That is the one. And the third one is, probably I missed it. And then you said the saving is around $1 million in one of the slide. And so I want to know what is the budget for that particular breeding program, and then how you drive it will just save $1 million, or probably I missed it. Thank you very much.
Yeah, no, great. So yeah, that's it. That's a good point. I think you cannot say, okay, with the Artemis there will be no human error. We're just saying, okay, if it's today 50%, for example, of the error is due to, you know, measuring mistakes or, you know, miswriting or those kind of things, that will probably reduce maybe from 50 then maybe to 10 or something, right? Because yeah, there will still be human error somewhere, I think, in that system, because humans are still, of course, involved. Yeah, the other thing is based on that information that we received. And again, this is something we need to understand a bit better. And I think this community is like a perfect case for that. And maybe this is a good moment to, yeah, to extend an invitation to anybody who's listening here to, you know, to reach out and say, okay, I want to know more. I want to contribute more to the knowledge around this. We really like to understand this, especially the element of the error and what is the effect on the breeding cycle. So to the people that we've talked to and the people that we are working with, it looks like there's quite some errors in the kind of the phenotyping data that is being collected, to the extent that, let's say, out of the 6 trials, 1 trial is just basically thrown away, right? And that's what we hear. So if the error is so large, that basically means that you either have to repeat the trial, or you have to repeat part of the trials, and that's then extends the breeding cycle, because you have needed more time to do because you need to repeat another trial, for example, another season, which, if you have more accurate data, you wouldn't have to do that, right? So that's that logic there. And then that $1 million, kind of 800 to 40,000, again, it's a bit of the back of the envelope. It's more like order of magnitude kind of thinking. But if you can reduce the breeding cycle, if you then look at the net present value of what that generates by having whatever you're creating on the market faster, but if you then also have greater heritability because you have the more accurate, basically, ways of measuring, you also kind of generate better varieties, right? that perform better. So that combination of bringing it earlier to the market and having them better varieties, that actually generates kind of like a value. It's not exactly like the money in your pocket, but that's the value that you then generate if you then look at placing that variety over a variety that you would have created with just basically manual phenotyping, right? So because you do your phenotyping better, you have a better variety earlier in the market, and that is actually that 840,000, let's say between 500,000 and 1 million kind of value that you create for your breeding program.
Thank you. Any other questions or comments?
I have a question, Lord. Yeah,
Yes,
thank you.
please, go ahead.
About the training the model, do you need to train the model every time for each experiment or for each set of experiment? And what is the other question is about the cost of using AI.
Yeah, great point. Elena is here also on the call, and she's the ML Ops, the machine learning expert here. So correct me if I'm wrong, but you basically per trait, you need to train the model. So once you have it for that particular bean, then you have let's say a plant stand model, which you could probably also use even for cowpea. Then if you go to more complex traits like open flower count, that's a bit more complicated to do. So yeah, you need to probably perk then crop train different kind of models. So, and that's something that we want to address then with that foundation model. Saying, okay, well, if you can recognize a flower for a cowpea or for a bean, that's basically the same. So you don't need to train that model again. So at the moment, but we train the models for each and every trait. But when that foundation model works well, then it's not necessary anymore, and you could use that model for other crops. Elena, just jump in if I'm not correct. Second, you said, what was your second point again? Sorry.
About the cost of using artificial intelligence.
Yeah, I think, well, that's also an interesting point. You can look at the cost in terms of, the monetary value that for us, right? The most of those models that were out there today, the ones that I showed you, RoboFlow, etc., they're basically free, right? So they don't cost a lot of money to be used and adapted. But then, of course, there's a whole discussion. Okay, what is the cost of AI in terms of displacement of labor or environmental cost, etc. That's, I think, a whole different kind of box that we also should open and want to open as well. I'm not sure if that was kind of the direction that you were thinking, or if that's useful.
No, yes, it's in that direction. In that usually the models of AI are already developed, but we need to adapt for our specific needs.
Yeah. Okay.
And maybe that has some kind of cost, I guess.
Yeah. Okay. Sorry. Yeah, I get you. So, yeah, I mean, if you want to recognize a cat or a dog on the street, those models exist. That's just done. But the models don't exist for the kind of plants that we're working with, or to a level of detail that we need. So the Googles of this world have, again, let's say, worked on recognizing a chair and recognizing a table and recognizing this, but not on specific diseases or flowers of beans, etc. So that's what we're basically developing. We're developing that machine learning part that is relevant to the CGIAR, which does not exist in the mainstream. So yeah, that's the investment. That's most of the money goes into developing that, because if we don't do it, now who else wants to do that, right?
Okay, thank you.
And I see also
Kevin,
Violet
please.
added something in the chat here, so thanks, Violet.
Yeah, no, I wanted to just come in and And thank you for this work, Leonard. I think it's really a great start. I mean, maybe it's the 60-40 or the 80-20. I mean, now you hit it on the nail just in your last comment that, of course, we want to get to other traits that are even more difficult to measure. But just getting the basic traits that you've showed us today reliably measured and at much less human time or labor cost, I think will make a big difference in our ambition to have more phenotyping networks with multiple partners, where the challenge often is the labor, and then, of course, secondarily, the quality of that labor to measure traits. And I think we can have a jump, what do you call it, a step change in the quality of data with something like this. It doesn't get us where we need to get yet, but I think this is very encouraging, and it's already can be quite valuable as it is now. So, and also just wanted to point out, I mean, I'm very pleased. One of your last slides where you showed, how you're working with so many different crops already. And I know when you talked with us about it, it was like, well, I don't know if we can take on another crop. We've already got like 3, and now I see you've probably got 10 or 12. So
Yeah.
somehow you've managed to be inclusive and start working, and it also demonstrates the demand from CG for this sort of tool. So thanks, and yeah, let's keep working together on it. I certainly look forward to partnering on this activity.
Yeah,
Over.
thanks, Kevin. Great. Yeah, well, it's we're gonna reach out soon. Great.
Yeah, thanks. Lennart, there is a question in chat from Moses. How are the images processed to generate the plot level data? And do you have a Bruno version for bananas?
So that's that trait extraction. I showed the slide. I showed a slide on it. I don't technically know how that works. I don't know if maybe Elena is on the call. She wants to explain that. That would be great. Otherwise, I would have to.
Sure.
Oh, thanks, Elena.
Yeah, no problem. Yeah, so right now, the model gives us outputs on an image level basis. So let's say you have a plot and you take about 60 images, you'll get a value for each of those. And the way that we extract the plot level value is dependent on the trait that we're collecting. For example, if it's something like plant stand, where you can take a look at the whole plot within one picture, the picture that you get is at the plot level output, right? So it counts the number of pictures on a whole plot. That's the trait that you get. However, if you're doing something like open flower counting for the sake of getting 50% days to flowering that date, you have to do a little bit more, right? Let's say I feed the model 60 pictures and I get open flower counts for the different number of pictures. To get days to 50% flowering for that plot, I have to say, okay, if 30 of the pictures, which is like 50% of the plants, right, in that plot, because the plot has 60, if 30 of those pictures have at least one open flower, then give me a yes value. And then the earliest date where you have that yes value would convert to your the days that you have reached that 50% flowering period of time. And then you just you get your days by subtracting from the planting date. So this is what we call on our side like our trait extraction pipeline. Depending on the trait that we have and the imagery data collection method that we use a different data science or analytics pipeline to get the plot level value.
Thank you, Elena. Do we have, okay, we have another question in chat also from Camilo. If I have my self-based data, is it possible to import it to the app and only test models to predictions?
I think we have to see that. But one of the things that has been maybe the most, maybe a challenging starting point is how do you take a picture and from what angle and from what frequency and of what do you take a picture? So having a lot of pictures just randomly is is good, but probably not good enough for what we're doing. So we've started. The starting point was the standard operating procedures of how do you take those pictures. And again, the Bruno is then easy because you say the height is always at this height, the angle is always like that. You drive around like this, so you have basically always a standard way of taking pictures, which again with handheld is another challenge. So yeah, maybe you can write an email to us and then we can look at that. There's another project that we're doing called Image Safari, where we're actually looking at diversity of images. From that purposes, it may be very useful to make the models more robust. But I think having the core machine learning is kind of like more standardized pictures. But yeah, this can be interesting more for the robustness of the models. But I think we have to. It would be great, Carmelo, if you could reach out. I can write my email here.
Okay. Yeah, thank you. That was gonna be my question. How can the breeding teams partner with you?
Yeah, so again, we are still, especially on the error issue, we are really, it's anecdotal evidence kind of that we're kind of drawing from, and we would like to know more. So if there are people interested in directly working with us and providing some intelligence around that, please reach out. Otherwise, I would also like to ask you, Dorcas, if maybe we could use this network also to send out maybe a Google survey for some of the things that we're just not finding any data on, but that we need to rely on some expert knowledge like the people that we have in this group, right?
Yeah.
And then, like I said, around the Science Week time, is it April, we should be launching some of the products, and then you can, we're at a more mature level where we can really look at, okay, how others can benefit from this and how the foundation model works and how you can develop your own applications based on this. I think that's a more of an exciting time, really. So yeah, keep an eye out, I would say, and just reach out to us, right? We are.
Okay. Thank you. One final question from me. What kind of traits would you say you are almost ready to scale? And are there any innovations for more complex traits, for example, for below ground traits or things like that?
Yeah, great point. So the counting traits, those are mostly the most easy, like plant count and flower count, how many flowers, how many pots. Those things are kind of made for computer vision, right? We are now venturing a lot into the element of disease as well. Some of the key diseases in potato or sorghum or beans. There's another project going on called Radar, where you basically look at underground phenotyping. So looking at the volume, for example, of cassava. And yeah, that's still pretty experimental, I would say. It's still difficult. I think the ambition is to say, okay, can you kind of correlate the above ground phenotyping with below ground? I would say we're still in that kind of discovery phase of how that can be done at scale in a feasible way. It's still challenging, I would say.
Yeah.
But exciting. That's why it's science, right?
Yes, definitely.
Otherwise, it would be boring.
Yeah, I agree. So thank you very much, Lennart, for the presentation. Of course, we will continue collaborating on this. Phenotyping at scale is really something that we're interested in. And so, yeah, we're always looking around for how can we achieve this innovatively. So let's keep the engagement and let's continue the conversation.
Okay.
Thank you, everyone, for the team that is joined. Julie, our communications persons, will have a page with the presentation and the recording that we'll share. Thank you.
Thank you very much.
Yeah.
Gracias. Bye-bye.
Thank you so much. Hi,
Thank
Buka.
you.
Great to see you here also. Yeah, nice.
Mm.